Another example here is the integral of x cubed plus 2 over x squared minus 1. So in this case, we have, if you look ahead a little bit, there's going to be a problem that arises. If I did partial fractions immediately, the numerator of the original fraction has x cubed in it, but the partial fractions only have x squared. So that means I'm not going to ever be able to set the like powers equal. I won't be able to find something to set equal to 1 for the coefficient of x cubed. So I can't set the coefficients of like powers equal. So whenever you have a higher degree on top of the original, what you need to do is actually divide out first. And by that we mean long division of polynomials. So I went ahead and showed the long division of polynomials. I kind of like to see the whole thing. You can also do synthetic division if you're good at that, which is exactly the same process. It's just that you don't have to write the powers of x every time, but I like to write them to see them. So I'd take x squared minus 1 and I put that into x cubed plus 2. So this is dividing x cubed plus 2 by x squared minus 1. And then the long division, the first thing I can do is multiply x squared by x, which gives me x cubed. I write it underneath. Minus x, because I have to multiply the whole thing, x squared minus 1 by x. And then I subtract that. So what I'll have is x cubed minus x cubed, 0. And I'll have, there's no x term in the top there, so I'll have 0 minus minus x, so it gives me an x, and then I have 2 minus 0, gives me a 2. Now x squared can't go into x by multiplying by a power of x, so that's my remainder, x plus 2. Alright, so you need to be able to take the answer and use it to rewrite the original fraction. The original fraction becomes x cubed plus 2 over x squared minus 1. It's equal to the quotient that we found, x, and then what's the remainder do? Well, that gives you another fraction. So it's equal to x plus the remainder, x plus 2, divided by the original denominator, x squared minus 1. Alright, now I can work it because now I can integrate x easily, and then x plus 2 over x squared minus 1 is going to be a partial fraction problem that I can do. So let me go ahead and work that out. X plus 2 over x squared minus 1 is equal to, factoring the bottom, x plus 2 over x minus 1 times x plus 1. And this is a pretty quick partial fraction because both of those factors underneath are linear, just degree 1. So I just need the constant a and b. Alright, to get the common denominator, I'm going to have to multiply the a by x plus 1 and the b by x minus 1. And then when I finish adding together the two fractions on the right hand of that equality, and then just look at the numerators because the denominators will be all the same, I'll have x plus 2 equals a times x plus 1 plus b times x minus 1. Then multiply through by the capital A and the capital B, collect like terms, and then set the coefficients of the like powers equal. So I'll have a plus b equals 1 and a minus b equals 2. Those are ready to add. I added those two equations. I didn't put the bar underneath them, but you can just add top to bottom so that you get 2a, b minus b is 0, and 1 plus 2 equals 3. Then you get a equals 3 halves, and plugging back into the first equation, you get b equals negative 1 half. Alright, I finished the problem over here. We should look back up to see where those came from. The original problem had x cubed plus 2 over x squared minus 1. But that equals x plus 2 over x squared minus 1. And so I put in the x, and then the second fraction decomposed into a over x minus 1, which was 3 halves, and b over x plus 1 minus 1/2 over x plus 1. Yay. And now I can do all three antiderivatives. X is just raise and divide, x squared over 2. Then I need to take the natural log of the absolute value of x minus 1 and keep the 3/2 out front, and the natural log of the absolute value of x plus 1, keep the minus 1/2 out front. On both of those natural logs, if there was something multiplying the x, like underneath there, I would have to divide by that number. But here it's just divide by 1 because it's 1x minus 1 and 1x plus 1. And of course, double check if you want by taking the derivative.